Right, class. Good morning, all. So, as I have described so many things related to fatty acids yesterday, I am just continuing it from there where I left out. I have told you that fatty acids are having a carboxylic group at one of the end, that is the, I can say, head, and due to the carboxylic acidic nature, the fatty acids are having some hydrophilic character, and due to a very long chain of you can say carbons, right, CH3, CH2, CH2. So because of that, it is hydrophobic in nature. So logically speaking, the fatty acid is a kind of amphipathic molecule where both the hydrophobic as well as hydrophilic ends are available. And if you see, I told you yesterday that in a saturated fat, there is single bonds. Saturated fats are hardened fats, while when I'm talking about unsaturated fats, they are liquids. The reason is the presence of double bond. Now see, what happened is that when there is a double bond, this is about stearic acid, this is a stearic acid, and if you remember, stearic acid is a saturated fat, means saturated fatty acid, straight bonds. Now if you see the linolenic acid, where actually 3 double bonds were present, it produces a kind of distorted structure like this, right. Now you can understand when something is tightened, it is single bond and very stretched, it creates toughness. When there is a kinkiness because of the double bond, it prevents the actually disrupts the forces by preventing the tails. So you can see the things cannot come together, they are repelling each other, and that is the reason why unsaturated fatty acids or unsaturated fats are liquid in nature. Okay, so this is just now I told you that they have a carboxylic acid end, and they have the ability or they have the tendency to donate a proton. You can see over here, this is COOH group, right. When a proton is being released from them, this is a stearic acid. So when a proton is being released from a carboxylic acid end, it actually produces COO minus, carboxylate ion. Here it is written carboxylate ion, right. So this carboxylate ion, when this is one of the most famous example which is depicted in front of you. So when it reacts with an alkali, I can say sodium hydroxide, the sodium hydroxide's sodium ion will now attaches with COO minus. So this is somewhat the end is showing to you all. Now you can see over here, you can see at this position, right, COONA. What we call this as, one OH is one proton is removed from here, one OH is removed from here, one proton removed from here, this one, just like this, I'm just trying to bring it up. One proton is removed from here, one OH is removed from here, it releases a water molecule. You can see this water molecule, here it is below to it. So when this COONA, because of this COONA, this is sodium salt of fatty acid, right. So this is one of the most famous example of saponification, and this we call it as sodium stearate. Stearic acid is used, so you call it as sodium stearate. If palmitic acid is used, you call it as sodium palmitate, correct. So because of that negative charge, the polar portion of the fatty acid becomes more polar. That is the reason it attaches with sodium. Okay, and we just call them as soaps. This is what happens in saponification. The sodium salt of fatty acids, we call them as soap. They are considered as amphipathic because they have a polar hydrophobic, that is they have a polar hydrophilic tail and head, and tail which is hydrophobic. Fine, that is we call it as amphipathic. Amphi means both. So here, dear students, I am ending it up. In next slide I will be describing about more of waxes.